Hello, this is Jackie. I am Engineer Assistant Manager of CYBERNET system. Today, I am going to show you about a vehicle dynamic simulation and hardware-in-the-loop testing. Let's see today's agenda. Here we go. Today, our agenda will cover three major parts. The first one is CarSim. CarSim delivers the most accurate, detailed, and efficient method for simulating the performance of passenger vehicles and light-duty trucks. With 20 years of real-world validation by automotive engineers, CarSim is universally the preferred tool for analyzing vehicle dynamics. Developing active controller, calculating the car performance characteristics, and engineering next-generation active safety system. The second one would be the introduction of hardware in the loop. Hardware in the loop is a method that we could test our vehicle controller. We could use a real-time machine to make our vehicle simulation to real-time level. That will allow us to do more testing before our real car is on the road. Automotive engineers always use this kind of method to do the controller's validation and verification. In the last part, I will introduce you some of our user cases. You will understand how CarSim and the hardware in the loop could be implemented. Our users use this method to develop and test their product in R&D stage. After this brief introduction, let's go to the detail. We will start from the first item, CarSim. As we have mentioned, CarSim delivers the most accurate, detailed, and efficient methods for simulating the performance of passenger vehicles and light-duty trucks. CarSim has the full 3D multi-body dynamic vehicle model that could be in response of throttle, brake, gear, and steering. Environmental conditions include a 3D ground road surface, as well as aerodynamic and wind effects. The modeling and simulating technology in CarSim is from something we call VehicleSim. We also have a VS Visualizer as part of VehicleSim to show videos of the run and also synchronize plotting. The mass model in CarSim was originally developed for mechanical engineers in automotive industry and research labs. The intent is to reproduce the results that are obtained in proving grounds or on the highways, with the same agreement to get from test to test repeatability. The CarSim mass models are represented at the system level. That means that the vehicle data is intended to be either measured or calculated, and it does not depend on detailed knowledge of component materials. What we're trying to do is going to make sure that the simulated vehicle responds the same way to driver control as it measured. CarSim uses a combination of parameters and variables to represent the vehicle. As shown in the picture, we have dimensions that are measured from the vehicle. We also have tables that represent measurable properties such as suspension, kinematics, camber versus drums. There are outputs that you could get from KNC rigs or detailed suspension models in programs like SuspensionSim and ADAS. We could also build 3D tables for complex models like powertrain. Here is an engine map giving engine torque as a function of speed and throttle. We have this as part of an internal combustion engine powertrain. Some of the measurable properties could not only be measured by real KNC rigs, but also by programs like ADAS or SuspensionSim. As we have mentioned, CarSim is for system-level simulation. However, sometimes we have to build up the details of the component. We could use suspension sim to simulate the chassis response and import the results into CarSim. We could also duplicate the same testing scenario to validate the data we input to CarSim. In powertrain type, we have front-wheel drive, rear-wheel drive, and all-wheel drive. In each of these specifications in which wheels are powered, we have the option of being internal combustion, hybrid, or all-electric. That makes us the ability to simulate all kinds of vehicle powertrain. You could also see from the hybrid figure, we could manage the control between the engine, the battery, and the motor. CarSim supports almost all kinds of powertrain combination, such as motor drive EV, hybrid EV. You could use CarSim to implement the powertrain setting and the testing scenario. Use the power management control to decide when to use motor and engine. In the last few years, there's been great interest in simulating scenarios involving advanced driving assistance system, or ADAS. In this one, the blue hatchback with the yellow arrows on the sides is the ego vehicle. All the other traffic vehicles are represented as moving objects in CarSim. They can have basic physics controlling their motions. CarSim comes a database that has hundreds of simulations. We have 100 plus testing scenarios. We have about 40 plus vehicle datasets here that are based on 10 unique vehicle configurations. CarSim has extensive documentation. That's the help menu. Every screen has help button. There are about 140 documents. VS Command is the script language available in CarSim, trussing, biasing, and suspension sim. We could use VS Command to add some features that don't already exist in CarSim. For example, in this video, the truck goes up a road whose grade is adjusted dynamically to different intervals. This is not built in. We could use VS Command to design our own testing scenarios. Documentation is included in CarSim's reference manuals so that you can easily learn how to use VS Command. We also have the online video on YouTube to show you about how to script VS Command. The event could allow us to set up the scenario step by step. Using pending event to trigger each step of your scenario. That could also help us to verify that the test is pass or fail. CarSim, trussing, biasing are used worldwide by over 100 OEMs and Tier 1 suppliers, and over 200 university and government research labs. There are more than 2,600 active CarSim seats, not including driving simulators or students. In this slide, I will use a user case to show you how CarSim finds problems for your design. In this case, the user uses a unique steering system like recircular steering system. This animation shows a recircular steering system. The customer actually uses a multi-link arm to control the steering angle. The relationship between steering angle to pivot arm angle is like this graph, as a result of multi-link arm. You can see that the relationship between steering angle and pivot angle is highly non-linear. We hope then to build it in CarSim and see what will happen. After modeling, we test this vehicle with the vehicle dynamic testing, static steer test with brake arm. The procedure is that the vehicle is static with brake on and we will rotate the steering wheel smoothly. Brake on will make sure that the vehicle will be static in the longitudinal axis, so that the torque in z-axis will have a bigger impact. You can see from this graph. The x-axis is the steering angle and the y-axis is the steering torque. The key point is the slope between steering torque and the steering angle. In vehicle dynamics, we call it steering gradient. The steering gradient will show whether the steering wheel is good to drive. As you can see, we have lots of rapid increasing or decreasing in steering gradient. This makes the vehicle hard to drive. For customer who is starting autonomous vehicle, this helps them find the problem. They knew that the steering system is very hard to control for their controller, but they never found that the problem is from the bad steering system. We help users compare to real target and find this problem, improve it, and solve it. Help them reduce the time in the end. The next case is the Pirelli. Pirelli used CarSim to test about a new tire model. There are two testing procedures, with the same distance to compare the fuel consumed, same throttle command to compare the travel distance. We can imagine that if we want to test this in a real world, we need two teams to maintain the vehicle condition, doing their best to make sure the vehicle shows no difference except of tire. In the same time, these two vehicles will always have some differences. For example, the engine will have difference since that the mileage is different. The test environment cannot always be the same. Sunny day, rain day, dry, or wet can have impact for the testing result. All of these variables can be controlled in simulation. We can have a totally same vehicle except for tires in CarSim. The simulation difference is a fully result of the tire model's difference. They use CarSim to save lots of human costs and vehicle maintenance. What we have mentioned, what we have introduced in previous slides is software simulation. Testing controller with software is something we call software in the loop. However, we still need to put our controller on hardware and test it with a real vehicle. Testing with real hardware is something we call hardware in the loop. Not only test about the control algorithm, but also test about the communication interface. Before we dive into hardware in the loop, let me introduce you the model-based design. Model-based design is a method. This method is used in controller development and testing, which are based on the response of plain model. Okay. It's also used in various kinds of industrial fields, such as aircraft, power grid, vehicle battery, and so on. Model-based design is useful for product evaluation, system integration proposal, controller design, and development. We can say that basically everything in the world can be a plain model. We could develop a controller use model-based design. Okay, now we have a new name, plain model. I will explain you what is plain model in the next slide. What is the plain model? I could assume that everyone here knows that force equals to mass multiplied to acceleration. If I put a force on a mass body, it will have a specified acceleration. That mass body is our control plane model. We can say that if the model is accurate enough, we can know the acceleration value in any time. We can develop a controller to control the acceleration value based on the mass equation. By using model-based design in CarSim. We could build up a lot of controllers. For example, ABS controller, semi-active suspension controller, ESC controller, and ADAS controller. As you can see in the video, most of these controllers are requested to be tested and pass dangerous situations, rollover, loss of control, difficult road situation, or obstacle avoidance. Controllers need to be tested in this situation to make sure the performance. Using MBD and the CarSim could help you test in early stage with low cost and save you money. However, if we just test our controller in simulation, there will be some pros and cons. Of course, we could say that with simulation, we could do the control algorithm verification. The controller could be tested in very early stage, and this is what we call software in the loop. However, the real controller has some physical limit. For example, the CPU have limitation on calculation power. The sample rate is limited by both hardware and the communication protocol. In the same time, real controller would be impacted by noise. Automotive engineers should do lots of hardware testing to make sure that the controller could be used on the real vehicle. Now we could have a full view between simulation and real testing. For simulation, we could have a safe testing environment. The testing is quick and could be tested in very early stage. Software in the loop is much cheaper than real vehicle testing and could be done in lab, run 24 hours per day. However, some of the requirement is assumed ideal like communication. On the other hand, the real testing could test the full, complex, and maybe the worst environment. It needs real testing field, costs lots of time, needs lots of human resource. And yes, we do need to care about public safety. As a result, the cost of human resource and hardware maintenance will be incredibly high. The question is, do we have a much balanced method to test our controller hardware? Of course, the answer is yes. That's why we use hardware in the loop. The hardware in the loop, as known as here, is a controller design and testing method. Let's assume that we have a controller under testing. The controller has to receive some signal from a real car. For example, ABS controller will have to get the fuel speed from a real car. Then, the controller will calculate the control command and send it out, just like the ABS controller will send out the brake control command. The different point is we will connect these signals, inputs, and outputs to a real-time simulation platform, which is running CarSim. Now you might want to ask a question. Why here? We could test the control algorithm in our computer, and this is why we have introduced the software in the loop. The difference is here consider more about the communication rate and the hardware performance. For example, what if the controller works worse when communication rate is slower than expectation? What if our hardware have some faults and bugs? A real controller will communicate with sensors and other control units. It might receive data from VCU and generate command to brake system. In different situations like high temperature, wrong connection to power supply, or receiving errors from other control units, will change the behavior of your controller. This kind of condition will probably be happened only when you test your controller in real car. And hardware in the loop can help you solve this problem in early stage. The second question you might want to ask is, how can HEAL do that? First, HEAL systems work in real-time OS, which can make sure the calculation rate is the same as real-time. Meanwhile, HEAL bus can support different kinds of communication I/O card. You might have lots of communication channels like CAN, link, digital I/O, and analog I/O. HEALbox can help you to use this I/O without any delay. We can also set some simulated fault signal to test your controller. Last but not least, HEALbox can decrease the time you spend on real-world testing. Okay, so let me explain it to you with a more easy understand method. Assume that we are a baseball player. When the ball is hit, we would probably start to react and try to catch the ball. At this moment, eyes are our sensor. Okay, now the ball is flying directly to us. We will start to think about that. How to catch it? What should I do after I catch the ball? Should I pass it to the first base or the second base? Our brain works as the controller trying to give a base command. The last step is start to do. Run, jump, try to catch the ball. That is what controller command is for. Give the command and make the actuator move as designed. Now, what if there is something wrong with the sensor? For example, on the curve, we might sometimes lose concentration instead of focus on the curve. For controller, the sensor might give the controller wrong data, delayed data, data with noise. This kind of incorrect data will change the control algorithm result. The controller might have its own problem either. Like sometimes we couldn't decide to pass the ball to first base or second base. Too many conflict information or data might slow down the controller's decision. On the other hand, since that controller has its physical limitation on calculation power, it might get slower and slower when we put lots of math calculation on it. The best situation is we choose a controller that can work with our control algorithm. Over-design power or under-design power is not what we want. Furthermore, the command also has chance to get some wrong action. For example, we might sometimes lose control of our muscle, couldn't coordinate our body. For controller, it sometimes couldn't have the correct response. Mechanical friction, noise, bad tuning, control algorithm. There are lots of reasons that the command couldn't work as designed. All of these questions will probably not happen in software in the loop. Only if we use hardware in the loop testing can the problem be shown and be solved. That is the reason why we use hardware in the loop. Let's summarize hardware in the loop. Hardware in the loop could not only help us implement our control algorithm, train model, and the simulations, but also integrate the interface of sensor data and the control algorithm, so that we could connect our controller hardware to simulation software. In vehicle application field, you could use CarSim and hardware in the loop platform to test your controllers. With the HEAL testing, we can use the simulation tool to different kinds of application field. We can develop autonomous vehicle by testing with ADAS controller via HEAL method. With CarSim RT and the sensor module, we can develop not only ADAS but also autonomous controller. Vehicle dynamic controller testing and validation can be implemented with different kinds of testing procedure. Trace control, ABS control, or four-wheel drive control can all be tested with CarSim. We can do simulation with very low cost and reduce the time we need for tuning and verification. We can also use simulation tool to do subsystem testing. Sometimes we will want to evaluate different subcomponents on the same car. For example, which brake system is suitable for my target? We could build different brake systems in CarSim and test it with the same car. Okay, so I will going to introduce some user case for you. The first case is for vehicle design. Our customer use TruckSim's example as a template. TruckSim have PBS testing procedure as example. Our user import their vehicle model and use it to test about the vehicle performance. The interesting point in this case is the trailer. A tractor with trailer is very expensive. If there is any crash or accident in real-world testing, there will be an unbearable cost. However, we can test it in simulation to evaluate the performance of our target. In this case, we use Pricing RT, Opal RT, and Python to build up an automatic hill testing. Since that Pricing support the component after model control from Windows, we use Python script to open Pricing, load the model to target, and execute the simulation. As a video, I ran the Python script from command line in Windows. After a few seconds, the pricing software will be opened. Since this is an automatic testing, you can see that there is no need to use mouse or keyboard to set up the simulation. When the auto setup procedure is done, the simulation will start running. This kind of auto simulation is widely used for hardware testing. You can use Python to build a full testing schedule. Full testing scenario includes hundreds of testing items. The next one is a hardware in the loop case. We use Pricing RT with Opal RT target to simulate a real bike. We also use NRT, which is a motor real-time simulator. In this case, we connect the real-time target to the real throttle handler and send the throttle command to the motor control unit. The motor control unit will send motor command to NR2, the motor simulator. Once the motor torque is sent to Pricing, the bike in Pricing will be ridden, and generate a vehicle speed which is going to be used to transition the motor. As you can see from the video, the engineer on your left-hand side will ride the bike. You can see the loading torque of the motor on your left, and the virtual Pricing bike is ridden on your right. This is an EV powertrain system hill testing. In this case, we build up a dynamometer testing environment with CarSim RT. On your left-hand side, CarSim RT is used to generate a testing schedule. We use FTP75 in this case. CarSim's driver model will send the driver command out to the under testing powertrain system. After receiving the command, the motor will start to generate a torque in order to push the vehicle in CarSim and also the dynamometer. CarSim will calculate the vehicle speed as a result of motor torque. This speed is used as a command for the dynamometer. The dynamometer will transition to the under testing motor to fulfill this testing system. Our user tests their motor control unit with this testing system. This can prevent lots of dangerous and costs because we can test it in the lab. The last example is the driving simulator. We built this driving simulator with CarSim RT, motion tuning, and a 6DOF motion platform. The motion tuning is going to implement the feeling of acceleration on the 6DOF motion platform. A real vehicle is running in an infinite world so that we will always have acceleration, velocities, and positions change. However, the motion platform works in a finite position. Every DOF has a limit. How can we use it to generate the result of a real vehicle? Motion tuning is using to solve this problem. The idea is humans cannot sense changes with very low frequency. If the vehicle dynamics change in a very low frequency, motion tuning will use gravity to compensate the feeling and put the motion platform back to the origin. That gives space to motion platform for next rapid moving. As you can see, when the vehicle is turning, the motion platform is moving to generate the acceleration feeling of the real car. Let's conclude for today's topic. At first, we talked about vehicle dynamic modeling with the introduction of CarSim. We also talked about the controller plane model. Then, we introduced the hardware-in-the-loop testing method. Hardware-in-the-loop is the advanced testing environment. Automotive engineers use this testing method to decrease the cost of time, the cost of human, and the cost of money. All of this is to improve the efficiency of product research and development. That's all for today's topic. Thank you.